Actually, the reason for Baladi's anomaly is a property called as stack property. So we shall examine with examples the same example what is stack property, and then I'll tell you. Okay, let's finish it, then I'll tell you what it is. Okay, now let's take the same reference string and let us say I'm going to use this initially optimal algorithm. Okay, so now I'm talking about optimal, and this is the reference string, and now I'll see what is the state of the memory in case if I have 3 frames. I mean, after every reference I'll show you what will be present in the main memory 3 frames. Okay, with 3 frames. So initially when 0 is referred, 0 will be present, and I'm talking about 3 frames. Okay, when 0 is referred, 0 will be present in the main memory frame, and when 1 is referred, 0 1 will be present, and 2 is referred, 0 1 2 will be present. Since there are 3 frames, this is the maximum that our memory can hold. Now when 3 is referred, one of them have to be replaced, right? Then according to this optimal algorithm, which one will be replaced? It will search and it will see which one will not be referred further. If you see 0 and 1, they are referred immediately, but then 2 is delayed. Therefore 2 will be replaced with 3. So after this reference, our 3 memory frames in the main memory will contain 0 1 3, right? And then 0 is referred, it is already there, and then 1 is referred, it is already there, right? And now when 4 is referred, again the same thing will happen. Now we have to check in the main memory which one will not be referred for the farthest, right? So 3, if you look at it, it will not be referred for a long time. Therefore when 4 has to be replaced, 4 has to be brought in, 3 will be replaced with 4. Got it? Let me just differentiate the reference string. Fine. And now when 0 is referred, 0 is already there. So 0 1 4, nothing changes. 1 is referred, 1 is already there, nothing changes. When 2 is referred, one of them have to be replaced, right? And now see this, when 2 is referred, only next required is 4. 0 and 1 both are not required. So let us say when I have a choice like that, when I could replace any one of the 2 frames, 2 pages, let us assume that I am going to go with the first one, which means when I have 0 and 1 to be replaced, let us say I have written in code in such a way that 0 is replaced always, or the first frame is replaced always. When I have choice, if I have many choices, I am going to take the first choice, right? So in this case, when 2 is required, I am going to take 2 1 4, and now again 3 is required, right? So what is the choice I have? I can either replace 1 or 2. So again I am going to take the first one. Therefore 2 is replaced and I got this, and 4 is required, 4 is there, right? Now this is the state of the main memory frames when I have exactly 3 frames. Now I want to observe for the same reference string, for the same algorithm, optimal algorithm, what happens when I have 4 4 frames. The number of frames are 4 now. Let's see that. So if the number of frames are 4, initially when 0 is referred, 0 will be there, right? See, I'm just talking about 4 frames. When 1 is referred, 0 1, and when 2 is referred, 0 1 2 will be there in the memory, and when 3 is referred, see, now since I have 4 frames, I'm talking about 4 frames. Since I have 4 frames, I need not go for replacement now. I still have a empty frame. Therefore when 3 is referred, 1 2 3, see, I am here, 0 1 2 are already present. Now 3 will be placed in the new frame. Got it? And now when 0 is referred, 0 is already there. Therefore 0 1 2 3, and when 1 is referred, 1 is already there, 0 1 2 3. And when 4 is referred, now 0 1 2 3 are the 4 frames present in our memory. Are you understanding this? See, this part indicates what happens when I have 3 frames, and this part is indicating what happens when I have 4 frames, right? In the earlier example also we did the same thing, but then I didn't show you at exact instances of time what are the contents. But here I want to save the contents at every instance of time, so that later I want to compare them, right? Earlier I was just interested in finding out the page fault, so I didn't show you this diagram, this kind of diagram. Okay, and now here when 4 is required, one of them have to be replaced. Among 0 1 2 3, one of them have to be replaced. So see this, 0 1 2 3, 3 is the one which is referred last. Therefore 3 will be replaced with 4. So what I get, 0 1 2 4. Got it? And next, when 0 is referred, 0 is already present, so nothing changes. 0, 1, 2, 4. And 1 is referred, when 1 is referred, 1 is already there, so nothing changes. And when 2 is referred, 2 is already there, so nothing changes. And when 3 is referred, 3 is not there, so which one are you going to replace? I told you, see, when 3 is referred, I just want 4 next. I don't want either 0 or 1 or 2, right? So you have 3 choices. I told you that whenever I have 3 choices, it is not the algorithm, it is the implementation. I implemented, let us assume that, it is an assumption, right? Let us assume that I am replacing the first one. Algorithm says that you can replace anyone, but the implementation, which means I am assuming that I'll always go for the first replacement, which means in this case I'm going to go with this. So I'm going to replace 0, which means I'll get 3, 1, 2, 4. Got it? And next, when 4 is required, 4 is already there, so nothing changes, right? So now these boxes, each box indicates what is the state of the memory when I had 3 frames and when I had 4 frames. 3 frames, 4, 3, 4, like that. Now if you observe it, for this algorithm, always the number of pages which were present when we had 3 frames are also present in when we have 4 frames, which means the number of pages, right, which were present with 3 frames are always present, right, in the frames when we have 4 frames. Now check this. See, 0 was present when I had 3 frames and 0 is present when I have 4 frames also, and 0, 1 is present here, 0, 1 is present here, 0, 1, 2, 0, 1, 2. Now check this, 0, 1, 3 are the pages present in 3 frames. Similarly, when I had 4 frames, then 0, 1, 3 are present in 4 frames also, right? And now check this, 0, 1, 3 are present when I had 3 frames, and again 0, 1, 3 are present here as well, right? 0, 1, 3 and then 0, 1, 3. 0, 1, 4, 0, 1, 4, 0, 1, 4, 0, 1, 4, 0, 1, 4, it is also present, isn't it? I mean, I am getting one more extra frame, extra page, but the concept is whatever pages were present earlier are now present in now also, right? So 0, 1, 2, again 0, 1, 4 and again 0, 1, 4, 0, 1, 4, 0, 1, 4, 2, 1, 4, 2, 1, 4. The order might be different, but anyway they are present. I am not interested in finding out the order. I am just interested in knowing the fact that whenever I increase the number of frames, the pages which were present earlier are also now present in the extra frames, isn't it? So 314 and again 314, 314 and again 314. Got it? Therefore, this property is called as stack property. Stack property is this one. This is stack property. If I have some number of pages in the main memory with m frames, and when I increase the number of frames by 1, right, then the same number of pages which were the same pages which were present when I had m frames should also be present when I have m plus 1 frames. That is what is a stack property. So optimal algorithm clearly is following stack property. So whenever an algorithm follows a stack property, okay, how can I declare that optimal algorithm follows the stack property? It might so happen that for this example, it might be true, but then for other example, it might not be true, right? But then mathematically, it has been proven that optimal algorithm, but that proof is very, very long, so don't get into it. So optimal algorithm is a stack algorithm. So, and the next rule is whenever an algorithm is stack algorithm, right, it always it doesn't fall into Baladi's anomaly, right? So optimal algorithm doesn't show Baladi's anomaly because it is a stack algorithm. Got it? Okay. So now let's see the same algorithm for the same thing with other algorithms also. Let's see FIFO next. Now let's look at the same example using FIFO, first in first out, and let's examine if first in first out behaves any differently here. Okay, for the same reference string. So the reference string is 0, 1, 2, 3, 0, 1, 4, 0, 1, 2, 3, 4. So for this reference string, let's see what happens by using FIFO. Okay, first in first out. So for FIFO we have to maintain even a queue, right? So let's examine the FIFO algorithm. I'm talking about this with 3 frames. So with 3 frames, when 0 is referred, with 3 frames initially when 0 is referred, then 0 will be brought into the memory, and then when 1 is referred, then 0 1, and when 2 is referred, 0 1 2, right? And when 3 is referred, so the order in which they have arrived in the main memory are 0 1 2, right? And when 3 is referred, then 0 has to be replaced and 3 has to be gotten, right? Then what will be replaced is 0. Therefore I get 3 1 2, right? And when again 0 is referred, then 1 will be replaced and 0 will be brought in. So which means I get 0 3 0 2. Are you following it? See, when 1 is replaced and 0 has to be brought in, then 1 is going to be replaced and 0 is gotten, right? And next when 1 is referred, right, then 2 will be replaced and 1 will be brought in, which means this 2 will be replaced and 1 will be brought in. 3 0 1, right? And when 4 is referred, 3 will be replaced and 4 will be brought in, which means in the place of 3 I'll write 4, right? And when again 0 is referred, yes, 0 will be brought in. 0 is already there, so no need of any change. And when 1 is referred, 1 is already there. And when 2 is referred, 0 has to be replaced and 2 has to be brought in, which means I get 4 2 1, right? And when 3 is referred, 1 has to be replaced and 3 has to be brought in, right? Which means when 3 is referred, 1 has to be replaced and 3 has to be brought in. And when 4 is referred, 4 is already there. Got it? So this is how this is the state of the memory when I have 3 frames. Now let me examine the state of the memory when I have 4 frames. So 4 frames. So initially when 0 is referred, it will be 0, and when 1 is referred, 0 1, and when 2 is referred, 0 1 2. But when 3 is referred, I need not go for any page replacement because I still have empty frames. Okay. So when I'm talking about when I have already 0 1 2 in 3 memory frames, and when 3 is referred, then I have one more memory frame available, isn't it? The reason is it is using 4 frames, right? Therefore 0 1 2 3. So this will be in the main memory, right? And now in the main memory, if you observe the queue, 0 1 2 3 is the order in which they have arrived in the queue, right? And now when 0 has to be again referred, 0 is already present, therefore there will be no change at all, right? And when 1 is referred, 1 is already present, therefore there is no change in the state of the pages in the frames. And when 4 is referred, now finally we have to go for a page replacement. Now what will be referred? 0 will be replaced with 4, which means in this case 0 1 2 3, the 0 will be replaced with 4. Then what do I get? 4 1 2 3. Got it? And when 0 is referred, again 1 has to be replaced with 0, which means 4 1 2 3, this 1 has to be replaced with 0. 4 0 2 3, right? And when 1 is referred, then 2 has to be replaced with 1. So which means in this 4 0 2 3, 2 will be replaced with 1, which means I get 4 0 1 3. Got it? And when 2 is referred, then 3 will be replaced with 2, which means in this place of 3, 2 will come. So 4 0 1 2, right? And when 3 is referred, 4 will be replaced with 3, which means this 4 will be replaced with 3, which means I get 3 0 1 2. And when 4 is referred again, 0 will be replaced with 4, right? Which means when this 4 is referred, 0 will be replaced with 4. 3 4 1 2. Got it? Now observe it, whether it is following the stack property or not. So what is stack property? Whenever you replace anything, whenever you replace any frame, then whenever you increase the number of frames, the number of pages which are present with 3 frames should always be the subset of the number of pages which are present in 4 frames. Now observe it. Yes, here it is subset, subset, subset. Here 3 1 2 are present with 3 frames, and 3 1 2 are present in 4 frames as well. Therefore it is subset. And 3 0 2 are present in 3 frames, and 3 0 2 are present in 4 frames as well. Therefore it is subset. 301 301, right? And 401, yes, look at this. In this case 0 is present here but 0 is not present here, right? Which means the number of frames which are present with 4 frames does not contain the pages which are present in 4 frames does not contain the pages which are present in 3 frames. Therefore it is not following the stack property, right? In fact here also, 401, but here 1 is missing, not following, right? 401 is there, 421, okay fine, 423, 4 is not there, right? And again 423, yeah, 423 is there. But anyway, there are some cases in which it is not following the stack property. Therefore FIFO, for some examples, it might not follow the stack property. That is why FIFO is showing Baladi's anomaly. Whenever there is missing the stack property, which means whenever any algorithm does not follow the stack property, it will lead to Baladi's anomaly. Got it? So the reason for Baladi's anomaly is stack property. There is no other reason. Only it is stack property. Okay. So that is the reason why FIFO is having this Baladi's anomaly. There might be questions like this. FIFO is having Baladi's anomaly because it does not follow the stack property. True or false? It is true. And second thing is, it is not always true that for every example it will not follow stack property. There will be some examples for which the stack property will be followed, but then there will be some examples for which it will not be followed, right? So in case if it follows stack property for all the examples, then we can, for all the reference strings, then we can say that it is following stack property, and we can say that it doesn't have Baladi's anomaly. But here Baladi's anomaly is possible, right? Fine. And now we have one more algorithm, which is the LRU, least recently used. We shall see that least recently used next. Okay. Now let's use the same reference string and let's see how the LRU behaves, and let's examine if LRU is having the stack property or not, if LRU is stack algorithm or not. Okay. So the same reference string 0 1 2 3 0 1 4 0 1 2 3 4. Okay. And now 0 is referred. So initially 0 is referred. Now let's talk about, this is LRU with 3 frames. 0 is referred, 0 will be brought in, and then 1 is referred, 1 will be brought in, 2 is referred and 2 will be brought in, and now all the 3 frames are full, and now 3 is referred. Now which one has to be brought in? The one which is least recently used. So 0 is least recently used, therefore 0 will be replaced. So I get 3 1 2, right? And now again 0 is required, and which one is least recently used? 1, therefore it will be replaced. 1 will be replaced, then I get this. And now I want 1. Which one is least recently used? 2. Therefore I am going to replace 2. 4 is required. Which one is not least recently used? 3. Therefore this is what I get, right? And then 0 is required. Which one is least recent? Okay, 0 is already present, no need of replacement. 1 is already present, no need of replacement. And then 2 is required. Which one is least recently used? 4 is least recently used, therefore 4 is replaced. And 3 is required. Which one is least recently used? 0. Therefore 2, the least recently used is 0, right? Therefore 2 3 1, and again 4 is required. Which one is least recently used? 1. So 2 3 4. Got it? Now let's see the same one with 4 frames. When I have 4 frames, 0 is required, 0 is brought in, and then 1 is required, 1 is brought in, 2 is required, 2 is brought in, and then 3 is required. So here I need not go for any replacement because I still have one extra frame remaining, right? So I can load 0 1 2 3. Got it? And next one 0 is required, 0 is already there. So 0 1 2 3. And when 1 is required, 1 is already there. 0 1 2 3, right? It doesn't change. The status is the state of the memory doesn't change. And when 4 is required, right, something has to be changed, which is here 2. So 2 is the least recently used, therefore 2 will be replaced. When 4 is referred, then 2 is going to be replaced. Then what do I get? 0 1 4 3. Got it? And when 0 is referred, 0 1 4 3, nothing changes, and when 1 is referred, nothing changes, and when 2 is referred, right, so the least recently used among all is, see, in the memory we have 0 1 4 3, 1 is referred, 0 is referred, 4 is referred, but 3 is referred at a long distance. Therefore I know when 2 is referred, 3 will be replaced, so 0 1 4 2. Got it? And next, when 3 is referred, right, so 2 is recently used, 1 is recently used, and 0 is recently used, but 4 is not recently used. Therefore least recently used 4 is replaced, which means 0 1 3 2. Got it? And when 4 is referred, then I know among 0 1 2 3, 0 is the least recently used, therefore 4 will be replaced, 0 will be replaced, and I get this, right? And now let's check this. Let's see if it is stack algorithm or not. So 0 is present in 0, right? I mean 0 is subset of this, therefore 0 1 is subset of this, and then this is subset of this, and again 3 1 2 is subset of this, right? See, 3 1 2, and then 3 0 2 is subset of this, 3 0 1 is subset of this, 4 0 1 is subset of this, 4 0 1 is present here, 4 0 1 present here, 2 0 1 present here, and 2 3 1, yes, 2 3 1 is present here, 2 3 4, 2 3 4 is present here. Therefore whenever I have 3 frames, whatever pages were present in 3 frames are also now present in 4 frames. So LRU is also a stack algorithm. See, actually by taking one example I cannot declare it, but mathematically it has been proven that it is stack algorithm, so you can trust me. So this one is stack algorithm optimal, and LRU is stack algorithm, but FIFO is not a stack algorithm. That is why FIFO suffers from Ballard's anomaly. Got it? So this is how Ballard's anomaly works. Fine.